Flip had arrived at her lonely North Pacific station on her first major assignment at sea. The wave sensor had been bolted to the hull of Flip and would reach the proper depth when Flip flipped. As the strange ship floods her ballast tanks and slowly tilts to her vertical operating position, all but 55 of her 355-foot hull sinks underwater to form a surprisingly stable base of operation. Flip is designed to heave up and down at a natural period which is longer than the longest swell. Consequently, she barely moves with waves, only 3 inches in a 30-foot sea. As she flips, the crew aboard shifts with her, walking now on what before were walls and rails. Jack Northrop operated the wave recorders aboard Flip while she was on station for a month. Wave measurements aboard Flip were comparable and in some ways better than those on land. Flip floated with negligible drifting, taking wave measurements for 3 hours, twice a day. After a 10,000-mile journey across the world's largest ocean, our waves, direct descendants of the waves born in the Antarctic winter, finally reached the shores of Alaska. Here, after their 2 weeks' journey, they finally die on the gently sloping beaches. The energy which had traveled across half the planet is at last expended in the breakers. The Alaskan station was operated by Gaylord Miller. He was the only one of us who sometimes met a bear on his way to work. At the Coast Guard station, Gay's recorders took a twice-daily record, the last look at our waves. It was here that our data would, we hoped, tell us how much of that energy had been lost in transit. When at the end of the summer we finally returned to California, we had amassed 10 million data points documenting waves from 12 major storms. A person with a desk calculator would have taken 2,000 years to convert this data into a meaningful picture of what happened. With a high-speed computer, our analysis was finished within a week of the end of the expedition. Bill Powers plotted day-by-day spectra. Plotting the spectra for the storm waves, we see a sloping ridge showing again the early arrivals in the low frequencies, followed on subsequent records by higher frequencies. This can be seen more clearly in a three-dimensional model. Here's the wave spectrum at Samoa for the morning of July 26. The peak indicates the earliest arrival of the wave group from our first storm. 12 hours later, the peak is bigger and has shifted to a higher frequency. Frequency increases from left to right. The same thing happens again with later spectra until the peak diminishes and disappears. The spectra for the entire wave group at Samoa show the storm as a slanting ridge starting at the low frequencies and ending in the high frequencies because of dispersion. The duration of the wave group at Samoa was 3 days. As we go to Palmyra, we see the same storm ridge, but it is more slanting because dispersion has stretched the wave train. Accordingly, the duration of the ridge has increased to 5 days. The data amassed from station to station shows that for this storm, we have succeeded in characterizing the wave climate across the entire ocean. On the basis of observations in Samoa, we could predict surfing conditions in Hawaii 3 days in advance. Our principal aim, however, was to learn something about the attenuation of waves, to compare the energy of the ridges from station to station. We found that the high frequencies were reduced quite a bit between New Zealand and Samoa, but not the low frequencies. However, attenuation from Samoa all the way north to Alaska is surprisingly small for all frequencies. There's no appreciable loss of energy across the equator, so my original conjecture about severe equatorial attenuation is wrong. Our observations and calculations now lead us to the following conclusions. Attenuation is largely the result of interaction between waves from the same storm. The interaction is weak once waves are well sorted by dispersion, and this explains why the attenuation is initially large and then negligible. The interaction is weak at low frequencies and strong at high frequencies, and this explains why only the high frequencies are attenuated. These observations are in general agreement with theory, and we are now one step closer to predicting waves from distant storms. In talking things over, we're pleased with how well these storms were documented by the experimental program. We are somewhat disappointed that the measured attenuation varied considerably from storm to storm, but this should be no surprise, for in nature, no two storms or no two waves are ever alike.